Oh, hello, 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 hello. Good evening. Thank you. Good evening. Hello, Dante. Thank you. Good evening, Alexis. Okay. Good evening. We'll be back. Good evening, Julia. Whoa. Okay. Oh, you're all here. That's awesome. I love this class. Okay. Good evening, Alexis. Good evening, Dante. Good evening, Juliana. Hello, Samantha. Hello, Charday. Good evening, Key. Good evening, Dante. Hi, Bree. Hello, Bradley. All right. All right. That's awesome. Thank you for thank you for being so understanding and on it. Oh, and Sade is showing a picture. That's awesome. Thank you. And Alexis is showing a new picture. Anyway, whatever. And there's like more animals per square. Okay, anyway, I'm not well, I'll save the silliness for another time. So wait, can you hear me though? Actually, wait a minute. No, you can't hear me. Wait, or I
Yeah,
can.
we can hear you. Don't worry, we can hear you.
Oh, you can. Okay, thank you, thank you. Okay, okay, great. Thank you, thank you. Okay, so right, this is an abbreviated class. Let me just make a couple things. I want to hear some things from you. I mean, I've heard some things already from Professor Talley. I gather things went well, but I know there were some questions or some concerns at the end. I'll try at the end of lab. I mean, I'll try to address them. Let me just blurt out a couple of things before whoa, is that what I meant? Well, sorry. Um, so one thing, hopefully it's clear to you that instead of the last 2 hours where we would normally meet, there has been a video posted. Let me be very clear about this. You know, it was posted around 3 p.m. So in theory, you could have watched it from 4 to 6 till now or whatever, but it doesn't matter whether you did or not. Just to be clear, the video that I actually posted in this little 7-point, wherever I announced that we were having a funny class today. And thank you all for all your communication back about that. Wherever that announcement was, I put a video in there, and it's called a video class 6A. Okay, that's the video where I do walk through the first 3 problems of the exam. I walk them through. I mean, some things I do in more detail, some things I do in less, but you know, I think it's about as direct and informative as I could be on the first 3 problems. Then I want to make it clear. So, you know, so you can watch that at any time. You could watch it this weekend while you're doing the exam. It's fine. But then I also want to make clear as far as problem 4, which is possibly the most new or unexplained problem of the whole exam. As far as problem 4 goes, I'm hoping to spend some time giving you an overview right here in this 45 minutes, but to whatever extent I don't, or to whatever extent I'm incomplete, just to be as clear as I can, the videos I just posted like 5 minutes ago, so it's called class 6B, class 6C, and class 6D. Those were all 3 different videos from last semester meant to address problem 4. Well, first of all, let me just ask, do you see them there? Do you all see video 6B, 6C? Yes, thank you. Okay, great. That's good enough for me. That's one person. It's more than one person. Okay, great. So I want to be clear what's going on there. So that's all about problem 4. Just in case I don't, you know, and I think between all those videos, it's a very detailed explanation of what I'm looking for problem 4. It's just that it's from last semester. Yeah, and I'm going to look in the chat in 1 second. Let me just blurt this out before I forget. But yeah, I see things happening in the chat. Just to be clear, like if you're trying to study the first 3 problems and what to do, like watch the video, you know, from today, 6A. If you're trying to understand what I'm looking for in problem 4, I would recommend watching those videos in that order. Like if you can only watch one video to help you with problem 4, I would watch 6B. 6B is all about problem 4, and it's the second like run through I did of it, so it's a little bit more polished last semester. 6C is the same thing. It's just an earlier version of the class, so it's just like slightly stylistically different. Maybe, you know, I say things in a slightly different way, just if you're trying, if something is confusing to you from 6B, maybe if you check it out in 6C, I might have said it slightly clearer, or you know, whatever. I might have emphasized certain things differently. But basically, B and C are 2 versions of the same thing. And I think B is probably the slightly better version. So check that out first. 6D is if you're really going to town, if you're trying to, like, you know, do everything you can. 6D backtracks to this business of the phase constant in the first place. The thing that we introduced at the end of yesterday's class, the extra term that was in homework 2, like the number 3.5 radians. And I made this big stink at the end of class yesterday that there can be an extra term in the cosine function. You need to understand that extra term, that phase constant, in order for all of problem 4 to make any sense. So again, in a second, I'm going to shut up. I'm going to look in chat and I'm going to just prioritize any concerns that you have right now or anything that was unclear in your lab collaborations and all that. Then whatever time I have, I'll try to give you a brief overview of problem 4 right now. But I'm just saying again, I think there's 3 videos that can help you with problem 4. I think between all 3 of them, I think you'll get what I'm looking for. And we'll all understand going in that that's the one that you have to do the most sort of original research and original thought to put it together yourself. Of course, help each other. But I'll know grading it that 4 is a different kind of problem from the other 3. All right, I'm going to now. So I hope that's clear. All right, let me just look in the chat. And I always, by the way, I always sound this intense and this crazy right before exams because they make me crazy too. I think you guys are probably fine, and probably a lot of you are a lot calmer than I sound right now, and there's no reason you shouldn't be. I'm just always jittery about time allocation, but I think you guys are fine, and I think you're going to be fine. And I certainly don't want to add to anybody's stress. Okay, let me look at the chat just to clarify. Oh, that's a great question. Oh my God. Sorry. Someone in the direct chat is asking the thing that we're doing right now, like whatever I'm talking about right now, will this be posted on YouTube? Good point. Yes, it totally will. I don't know. Yes. Yeah, it'll be, I'll call it lecture 6E. Yes, it will. I don't know how much we'll get done, but yes, good point. Okay, can I go over 1? Well, now here's the thing. Okay, so that's a direct track question 2. I am here to answer question. Okay, so to be super honest, yeah, I want to hear your questions before I just start talking, but I'm going to be a little bit careful about your questions just because we have limited time. So one question in the direct chat is, can I go over number 1 from the review from the practice test? That's totally fair question. And you totally would want to see me talk about number 1, but to be totally clear and honest, just in case it's not clear, I spend a long time going over it in the video that I just made this morning. That's posted as video as class 6B. Let me just say this more slowly. Like the video that I posted, like instead of the last 2 hours of class, instead of you being here, is me walking through pretty thoroughly problems 1, 2, and 3. I think it's like a 2-hour long video. I got so thorough and caught up in problems 1, 2, and 3 that I didn't get to problem 4. So, and you may, okay, great. Thank you for, the person in direct chat totally, please submit for points that you just closed the loop because now I feel better that you, yeah. So to everybody, I don't expect that you already know that you've already checked it out, but yes, I would highly recommend for anything in problem 1, 2, or 3, check out video 6A and understand, please, again, that's not from a past semester. That's literally directly to you guys, directly over this material. It's just that you're not participating during it. That's the only difference. But okay, so it specifically is problems 1, 2, and 3 with you in mind. So thank you for asking. Oh yeah, go. Yeah.
I know you say you don't want to dwell much on like questions about previous, but I watched the video, right? And in class earlier we had a little how would I put it? We had a little conflict when it comes to our answers. I watched your video, and you suggested it one way, but we also worked it out another possible way, but we get different answers. So if I can be specific, like when we calculated the period, some person did it like 2 pi, the period of a pendulum, 2 pi, square root of L divided by G. And they got a different answer compared to if we were to use, the period of 1 over frequency.
Okay, good, very good question. Hold on, I'm just answering a direct chat thing here, but yeah, so you're talking about, So when you say you had a little conflict in class, you're talking about in lab today. I think I heard about this. You're talking about in lab today.
Yeah, after we worked out, we spent time working out the practice midterm that you did. We went through sharing some of our answers and seeing how best they matched up, and some of them the procedures make 100% sense, but the answers just weren't mathing.
Okay, wait, I do no, that's a very good question. And this is one of the things one of the reasons we're here right now, definitely, is to try to clean up any unresolved issues or messes from the lab. That's totally on point. So hold on, I'm going to switch the screen sharing here for a second. Hold on. Okay, 1 second. Okay, no, this is a very good question. I'm going to screen share. I'm going to send you. Okay, hold on. You're talking about, and I'm also looking at chat. Oh, okay, great. You're talking about. Okay, and yes, again, whatever Christopher's asking about right now, whatever I'm saying, I'm so psyched that Dante's still here. Totally, this this will be posted as well. But I believe, and I believe Professor Talley told me about this. You're talking about this pendulum problem 2, right? And you're talking about part Roman numeral like lowercase. You're talking about this. What is the angular frequency of the oscillator on the string part, right? Where you got 2 different answers, where people got 2 different answers. That's what you're talking about.
Yeah, and we and also number 3, like Roman numeral 3, we calculated the period like 2 different ways.
Okay, I know what's happening here, and I'm so glad. Yes, I'm so glad you're bringing this to my attention. There is something slightly tricky about this problem, that it's not meant to be a trick, but there is something slightly tricky. And because of what you're bringing to my attention, I will make the wording, I will fix up the wording so it's more clear tomorrow. But anybody who's listening now will benefit greatly from listening now. Here's the thing about this problem, where it says at the top somewhere near the Earth's surface, and it really should, that's very ambiguous, the word near. I'll change that tomorrow. It's trying to say we don't know where this pendulum is. What's going on in this problem is we don't know until the end of the whole problem exactly what the rate of free fall acceleration of gravity is. Like it's not a given in this problem that G equals 9.8. The problem used to be very clear about that, and then it went through changes, and now that's not clear at all, and that's my fault, and I will change that. But what I'm getting at is this. A big purpose of this problem is that you're actually trying to derive by the end, and I do talk about this in the video, but obviously not everyone's seen this yet. You're trying by the end, by part 5 and then 6, you're trying to derive that for a pendulum, omega equals square root of G over L, or conversely then, that like capital T equals 2 pi times the square root of L over G. We don't know that at the beginning of the problem, and we don't know the value of G at the beginning of the problem. Now, again, that is not as clear as it should be. It's not clear at all, actually, and that's a fault of the problem. So I will fix that. That's why we're having this now, and I'm talking about this now. But so what I'm getting at is this. We're trying to discover in the problem that omega equals square root of G over L. And then by the end, we're trying to use that to actually find out what G actually is at this location. Because in fact, that is how we know what G is. We find it out through pendulums because we so strongly believe this proof that omega equals square root of G over L. So this is a long way of saying, and maybe I'll write it down in a minute. What I'm saying is the way, the reason you're right that there seem to be 2 different ways to do this, but they seem to both get 2 different answers, is that actually there really isn't 2 different ways to do this. The way that you're expected to do this or being asked to do this is just look at that differential equation, the one right in the middle of the page, and say, okay, that's the differential equation for simple harmonic oscillation. The the angular frequency omega must be the square root of that constant right in the middle there, pi over 6. So omega must be pi over 6. And you use that throughout the problem. And I know you know, or at least I know. I mean, I can tell by the way he's asking, and I know that Christopher gets that. What Christopher's saying to everybody is, yeah, but how come the other way doesn't work? The other way should work too. And that's ultimately what you're trying to show by the end. But this, we're not at the Earth's surface here. We're somewhere else where G is some other value. And that's what we're actually finding out by the end of the problem. So the one assumption you can't make is that G equals 9.8. It needs to be clear about that. That is my fault because the problem's changed so many times over the years. But so if you did it the other way in the lab, like you definitely understand something. And if you now understand both ways, you're good. But yeah, for tomorrow, what I'm cautioning everybody is the first thing, it'll be more clear, but you first and foremost want to know this differential equation and show from it that omega equals square root of G over L. Okay, that was too long, but does that make sense what I'm saying?
Yeah, that was perfect. Thanks.
Okay, thank you very much. Okay, oh, and I'm looking in the chat now. So, but again, I do apologize. Like, again, I'm glad we're doing this because, yeah, that's a little bit of my fault of the problem. And maybe tomorrow, like, who knows? Maybe tomorrow, if I'm really smart, I'll adjust the numbers so it totally is 9.8 and it all works. Maybe, I don't know. But what I do want you to know is omega equals square root of G over L. That's not a given going in. That's what you're proving by the end of the problem. So that's what. Okay, let me look in the chat. Hold on. Okay. Okay. I'll look at the. Oh, and Bradley, thank you for showing an image. Totally get points for that. Let me look. Hold on. Oh, and Key, both of you. Wait, was it? A quick question. Someone's in the chat just asked a quick question on the homework, and I still owe some of you more points on the homework. It's still not too late, even though we're about to have a midterm. You're getting graded on the homework for how thoroughly you do the 5-step method. Potentially you can get you can get full score eventually on homework without getting all answers correct. It's not about correct answers. It's about thoroughness of method on homework. But now on the exam, it's both for sure. I'm just answering a question in chat. And I'm going to look at these images in a second. Right. Oh, so Bradley and to everybody else in this question, and again, yeah, it's a little surprising. In this question, you can't assume that G is 9.8 unless it tells you to, and it won't tell you to in this question. I guess anywhere else in the test you can, but it doesn't come up anywhere else in the test. Do I know what the calculated value of G? You know what? Honestly, do I? Wait a minute. I might, but it's definitely in one of those. It's in one of the videos I posted, or it's in a past video. But I think I want to say, don't quote me on this, but I feel like it comes out to 2 point something. But if someone has an answer, wants to put in a direct chat, it might jog my memory. But okay, I'm looking. Okay. So yes, it's clear. Let me just look at these images really quick. But I have a feeling. I mean, again, I'm not proud of the mistake in that question. So it sounds like if this is your biggest concern, like you guys are very much on top of things. Okay, I'm looking at the image. Hang on. Right. So you know what's going on. No, you're good. It's just the main thing, and it's not supposed to be a tricky thing about G, but the main thing about this problem is you're here to show enough understanding of the differential equation that you're showing why omega came out to be square root of G over L. Because by the way, again, if you can do that, what you're really doing is you're showing from scratch, from raw physics, why you know that the pendulum actually is a harmonic oscillator, why it actually can be described by that differential equation. In other words, the real purpose of this problem and the real purpose of lab 2 is it's really a redo of homework 1, particularly the last question of homework 1. We're reinvestigating the whole same process where we use basic physics to describe this basic physical system, but then we see that physics leads us to this new and exotic mathematics. The free body diagram was easier with a mass on a spring. I mean, it's just like one horizontal force. So you didn't have to stress the free body diagram, but you were starting from a free body diagram and F net equals MA, and then you were going through and seeing, aha, there's this differential equation. Aha, this is harmonic oscillation. You're being asked to do the same thing now with a pendulum. That's really the purpose of the problem. So you can't start off by assuming that you already know that the period or the frequency work that way, because the purpose of the problem is but I think you see that. But yes, everything you're doing on the board, I mean, I'm looking at the image right now, is great if you make that assumption. I'm looking at the other board quickly. And just keep the things coming in chat. I'm just going to keep going in chat. Right. So I love that these two board pictures were put in the chat. And again, please submit for points for that fact. I'm saying the part of the board, and yeah, I see why the two answers don't jive, because G is not actually 9.8. But yes, your two methods are both independently correct. If you were correct. But okay. But again, if I lost anybody on any of this, again, if you watch video 6A, I walk through the correct way to do this problem, or the way I'm intending. So if all of this is going on, if you're like, I lost faith in all of this like 4 hours ago, just ignore all this and just follow the way that I'm recommending in the video. Okay. Yeah, no, near the Earth's surface is really misleading. Honestly, Bradley, it's a total mistake that I said that. It's hideously misleading. And it's honestly because we've changed this problem back for so many times that I actually forgot to change that correctly. No, you're right. I have no defense of that. It's hideously misleading. I mean, it's like wrong. Okay, so I apologize. Okay. Oh, now James has something in the chat. Wait, I'm just looking at the time. Okay, and again, since, this is all great. This is what we need. And again, if 645 comes and what we've done is like addressed all these kind of things, I do encourage you to watch all the videos on question 4. I mean, it is the hardest. We'll all know going in that question 4 is the hardest. Like, I'll know that you know that I know that. That's all. That doesn't mean I'm just going to, I still want you to work really hard on it and do your best, but it will be testing a different set of skills from 1, 2, and 3. It'll be testing how well you put together new material on your own, which of course is the next step. But anyway, what James put in the chat around the velocity, even with the different numbers. Oh, interesting. Even with the different numbers. Oh, God.
Yeah, because we did it, well, best Billy used, there were 3 different ways. Well, we basically had some answers match up, but they were like the different periods. We got different periods for sure. But for the velocity, we calculated it 2 different ways. I don't remember how the others calculated it, but I think I did the energy conservation method, and even with the different numbers, we came out with the same answer. So.
Yeah, that is interesting. What's happening with my? Well, let me say a quick thing about that. I mean, no, that is interesting. Right, there are 2 different ways to calculate the velocity, but even there, if you really look at this question is doing a lot. I mean, the questions progressively harder in the exam, as you can tell. The thing is, with the 2 different ways of getting the velocity, one overarching thing I can say to everybody is, since there are ultimately 2 ways, but the first way and they ultimately have to jive, yes, and that's ultimately what you're showing in part 6. However, the way I recommend, if anybody's listening to me right now, I mean, if you're just tuning in right now, the way I recommend getting the velocity for part 4 of this problem 3, the way I recommend getting the speed, my first way is take the derivative of the position function. In other words, use your solution to the differential equation. Maybe I'll write this down in a second. But again, this is what I do in the video. But take your solution to the differential equation. That's a solution for theta. It'll be something like theta equals theta naught cosine omega t, right? You take that solution. If you multiply theta by r, what you have is x, as in arc length, or s, you could call it, right? Don't ever forget, theta, by definition, is arc length divided by radius. That's what an angle is, right? So according to your differential equation, you have theta equals theta naught cosine omega t. Okay, that's what tells you what theta is at any given moment in time. If you multiply that whole thing, both sides, by r, you now have an expression for X. You now have an expression for where the bob is in the arc that it's swinging along. Like you literally have a position function for it. Now, theta itself is like angular position, but if you multiply theta by R, so in other words, if you write down theta naught times R times cosine of omega t, you now, that what that is X. X equals, I'll say it one more time. I can't write it because I'll switch screens. It'll take too long. But I'm saying X equals theta naught times R times cosine of omega t. That's your expression for X as a function of t now. X as, and again, not theta, but X, like where the thing is along its arc length. Well, why am I making a big stink of this? Because if you take a derivative of that, if you differentiate, if you take dx dt, now you have an expression for v. So now, right, so literally you take the different, you take the derivative of that, you'll get negative theta naught R, excuse me, you'll get negative theta naught omega R sine omega t. Again, I'm saying this all in space. You can play the video again later, but I'm saying if you differentiate that expression for X, if you get dx dt, now you have an expression for V. It's asking for you to find V at a specific time. What time? 1/4 of the period. You plug in the quarter of the period for that, and that will be your speed at where it's asking for. Now, I'm recommending to everybody, I'm looking at the time, I'm recommending that's the first way you should do it. That's the safest way. If whatever changes I make to this problem tomorrow, whatever confusions might be in your mind, that's actually, first of all, the safest way, and also the way that's most relevant to like all the math that we're learning here and stuff, because that way doesn't have any kind of G in it at all. You're just safe to do that. It doesn't rely on G. The other way, the energy conservation way, like, which you're ultimately going to check it against, you are ultimately going to check it against in part 6, but you got to realize that the other way involves a G. So, so that's why in the end, you're doing these 2 different ways and finding, what am I trying to say? Yeah, like if you want to do the energy way, you can't really do it until you have found the value for G. Then you can do like 1 FMV squared plus MGH is a constant, right? Let me say that. I'm going to say one more thing. I should be writing this down. I'm saying there's ultimately 2 different ways to solve for V at the bottom. I would do the derivative way first. I wouldn't do the energy way until I independently solve for G. How do I independently solve for G? Well, by the time you get to the end of this problem, by the time you've proven in part 5, by the end of part 5, you've proven that omega equals square root of G over L. Okay, and you have omega from the beginning of the problem. So you rearrange and say, okay, G equals omega squared times L. I will pause for a second to write this down if that helps anybody. But I'm saying use your omega to get your G by the time you're at the end of the problem. Then plug that G into your energy method and you'll show that both ways jive. I hope that makes some sense. I'm looking in the chat. Oh, yeah. Good. So what Bradley said in the chat, wait, I found a function for the angular displacement. Yes. What Bradley said at the end of chat is more concise words for what I just said. Like, yes, that's what I'm saying. If you understand what Bradley's saying in the chat, that I agree with it. That's what I'm saying. I mean, he's saying it better, but so cool. Okay, wait, where are we? Were there other, I'm a little concerned to ask this. I do believe Professor Talley told me was there one other issue that came up in lab of confusion? Was it, was there something else that wasn't resolved in lab? I'm good. No, we're good. All right. Do we feel like, can I spend 15 minutes overviewing problem 4 now? I mean, would that be the appropriate? Raise your hand if that would be helpful and desired. If I now spend the 5th, okay, great. Thank you, Christina. Thank you, Valentina. Thank you, Samantha. Thank you, Michaela. Thank you, Evelyn. Okay, that is good enough for me. Okay, and thank you, anybody else, Bradley. Okay, I see a lot of hands. Great, that's what I'm gonna do. And Again, I'll be a little bit fast, but it's a big overview, and then you'll check out the other videos and blah, blah, blah. Okay, so I'm switching screens. I mean, I'm switching. Yeah, I'm switching. Okay, so all these notes here are all the upload. Oh, I'll upload all this when we're done. All of these notes here, these first 14 pages, are all like from what I put up at video 6A. So I'll just continue. Okay. Okay. Now, what I will say is, even if I had all the time in the world, let me make this clear. I've got 15 minutes. Even if I had all the time in the world, what I would be doing right now is I'm giving you now my lecture material, like my conceptual understanding of this topic. So even in a perfect world, I'm not doing a 5-step method right now, or I'm just giving you the material. And then your job in problem 4 is to turn it back to me like in essay form. You'll notice problem 4, it gives you a certain amount of points for diagrams, a certain amount of points for math equations. Problem 4 is, in other words, it's not really traditional 5-step method. It's like more like an essay or a free response, whatever, okay? You've got to put this together and show that you understand what I'm about to explain. And I'm just going to now explain it my way. And I just lost everything. Okay, here we go. I'm just changing the view on the screen. Okay. So here's the thing. What we've established is I'm going to use the variable y now for a reason. You'll see. I'm going to picture a vertical spring. Okay, I'm going to picture a spring going up and down along the y-axis. So my variable here, you're used to me changing variables all the time. I'm going to use y here. What we established yesterday is that a solution, a way of describing a simple harmonic oscillator, sure, is like a cosine omega t. But what we established yesterday is that you can add this extra term called a phase constant to the cosine argument, and it still operates correctly when you take the derivatives. So what I first want to say, and this thing is, we call it a phase constant, and it's measured in radians. So what is it? Like physically, what's the point of this thing, and what am I going to do with it? The point of this thing, of theta, is this is a head start or delay. I mean, depending if it's positive or negative. It's so we can really say plus or minus. Head start or delay in phase, i.e. in the cycle. Now, again, I'm going to say this part quickly. And again, what I'm about to summarize right now, there's a whole, is all of video 6D or whatever does this in detail. But the point is, when there's no phi at all, when phi equals 0, that means there's no head start or delay in where the thing is in its cycles. It means that we started our stopwatch at the sort of most natural or most obvious point in the cycle. It means we started our stopwatch when the thing was at an amplitude position, right? Like in other words, that's why we got away. In other words, the assumption we were making all through homework 1, like when t equals 0 and v was equal to 0, the original mass on our original spring from homework 1 was all the way at its maximum displacement from equilibrium, 15 centimeters, right? But we could have started our stopwatch some other time. In other words, we could have started the time when the thing was already somewhere in its cycle, right? If, for example, if phi were pi over 2 radians, then if you just do the math and check this with the equation, if phi equals pi over 2 radians, when when t would equal 0. If we started our stopwatch when, sorry, if phi is pi over 2, then that means that then when t equaled 0, y didn't equal a, y equaled 0. If you think about it, because you know the cosine of 0 is 1. But the cosine of 0 plus pi over 2 is the cosine of pi over 2. Pi over 2 radians, 90 degrees, quarter cycle, right? Y would equal 0. So what I'm trying to say is if phi is always measured in radians, phi is the portion of the cycle. And again, you'll think about this more slowly and plug into the equations to test what I'm saying. What equation do you plug into? You plug into y equals a cosine omega t plus phi. If phi is a number other than 0, that represents what portion of the cycle the object already got into by the time we started our clock. It's a head start or a delay measured in portions of a cycle. So pi over 2 radians means a quarter of a cycle. That means the thing was already a quarter of a cycle into its oscillation when we start our stopwatch. Okay, that's what phi means. And if phi were pi, that would mean it's already a half cycle in. It's already at the other turning point by the time we start our stopwatch. That's what it means. It's a head start. It's an initial angular position, an initial place in the cycle. Now, that's what phi means. That's phi. It's a constant. And again, you can play a slower video on that if you want to see a slower explanation, blah, blah, blah. But phi is just a constant number that represents where the thing was in terms of the cycle once we started. Now, one of the reasons we never cared about this for the first homework or the first set of exercises, if you have one oscillator, why would you ever even buy? Of course, you would want to start your stopwatch at the most convenient place that you can. You can start your stopwatch wherever you want. So you would start it at the easiest, most obvious place when the object is at an amplitude position. Why would you ever bother with this? You wouldn't ever bother with this if you only had one oscillator. This phase constant idea becomes important only and always when you have more than one oscillator that are doing something identical in every respect other than where they started. If you have a bunch of oscillators that have head starts relative to each other, that's when this becomes relevant. And that's what we want to look at for 8 minutes. Let's say, consider that you have, and this is why this is called, consider that you have a collection of identical oscillators. So in other words, like you have an M hanging from a K, and you have another M hanging from a K, but it starts a little bit lower down. And you have another M. And they're all identical M, and they're all identical K, right? Let's call this one. Well, okay, so they're all hanging from a ceiling, or they're all on a lab table going up and down, whatever. They're all the same M. They're all the same K. And there's a whole bunch of them. And they're all vertical oscillators, but they're all spread out, let's say, on an x-axis. And let's say literally they're spread out evenly on the x-axis so that the first oscillator is at position x equals 0, like it's at the edge of the meter stick. And then the second oscillator, so that's really technically the 0th oscillator. And then the first oscillator is at position x equals 1, like 1 centimeter or 1 meter, whatever. And the next one is at x equals 2, et cetera, et cetera. Okay, so you have a bunch of identical oscillators, identical vertical oscillators, all spread out evenly on an x-axis, right? And the only difference among each of these oscillators is that each one has a different phase constant. For example, so this is an example now. Say the first one could be described by the equation. So y equals 0. So the first one could be described by the equation, y sub 0 equals a cosine omega t. Let's say, and I'm using y because there's a vertical oscillators, right? And then the next one, this one, y1 equals a cosine omega t. Let's say, sorry, yeah.
Is it? Yeah, I was about to say that. Could we just do them at intervals? So pi over 2, then pi, then
Exactly.
3 pi over 2 or stuff
Exactly.
like that.
No, you're totally on it. I'm rushing just for the sake of, and by the way, anybody at 6:45, I have to let you all go, but I will stay here for a minute if anybody wants to expand on this with me. But yes, so I'm sorry if I sound rushed, but he's totally right. He's totally right. And look, and I have to be very clear too, if we get cut off. What he's right about, the key point is this is a pattern that I'm on purpose setting up. I'm definitely on purpose setting up a pattern. And the pattern will be true no matter what the example is. In this example, I'm doing intervals of pi over 2. I'm just using that as an example for the moment. It could have been pi over 4. It could be pi, it could be anything. But yes, let's assume that the very first one the very 0th one doesn't have a phase constant at all. Like it's just starting to get that, the stop, it's at amplitude when the stopwatch goes. Then the next one happens to be at equilibrium when the stopwatch starts at 0. Like it has a head start. And assume the next one has pi over 2 compared to that. Oh, sorry, wait, so I did that wrong. Has pi over 2 compared to the guy before it. So that's 2 pi over 2 compared to 0, right? And the next one, just like Christopher's saying, the next one would be like omega t plus 3 pi over 2. Now, the pi over 2 is just an arbitrary example. I could have done any amount, any step I wanted. But the key thing to notice is if I set up a whole bunch of oscillators like this, this is what we call a collection of phase-staggered oscillators, right? If they're all identical in every way, except they're increasing or decreasing in phase by a constant step, right? If I did that, there's 2 important revelations, and then we'll be done, right? But just imagine, so I have a whole set of oscillators, a huge set. And of course, it would eventually, if I kept going, you could imagine the masses, whatever. If I had a huge set, eventually some of these masses would be higher than the one depicted. It would go up and down, the endpoints. So at first blush, I look at it, I'm like, okay, each one of these oscillators has its own equation to describe it. This is a huge number of oscillators. It's a huge number of equations. It looks like a nightmare. But if I realize the pattern that Christopher's pointing at, if I realize, well, wait a second, each one is increasing by pi over 2. And like, if I look at the oscillator that's at position x equals 2, it has a phase constant of 2 times pi over 2, et cetera, et cetera. So I could capture this whole thing, by writing something like, in this case, and I promise we actually are almost done for this overview. And you're going to just put this all in your own words and spread it out, but we're almost done in 3 minutes. But again, watch the other videos for expansion. But we could capture the whole thing by writing one big equation that would say something like this: A cosine omega t plus pi over 2 times x, right? This is what Christopher's saying, that like for any x that you plug in, any spring that you are looking at, you plug in how far across it is, and then you multiply that by pi over 2, that will be the phase constant for that spring. So this one equation now would cover the entire collection, right? And this one equation would be a function of 2 variables, x and t, right? Now we're almost done. Just bear with me for a second. 2 quick things I have to say about this. One, that's totally true as long as my step was pi over 2. But no one ever said the step had to be pi over 2. The step, that is to say, the amount that, right, well, hold on one second, just bear with me for a second. But yeah, that is the phase. Bear with me for a second. The step, the change in phase per delta x in this case, it's a constant number. In this case, it was pi over 2, but it could be some other number. Whatever it is, it's measured in radians per meter, like the amount of phase that you have per the number of meters over you are, whatever that is, let's from now on call K. Let's call that measure K, as in from lab 3. K with weird serifs on it. It's not the K of Hooke's law. It's a different K. It's a K that's measured in radians per meter. I'm just about done. I promise. We have 1 more minute. And the name for this K thing is called angular, not frequency, because it's not how much you increase through your cycle per time. This is how much you increase through your cycle in space. This is called angular wave number. Now, so I'm saying, and bear with me for like 1 more minute, I'm saying this entire collection of phase staggered oscillators can be captured with one big equation that you saw ultimately in lab 3. One equation like this, which is a function of x and t. Omega is angular frequency, cycles per time, and k is angular wave number. Why is it called that? Because if you stand back and look at this freaking thing, what you have is a wave. Duh. I mean, not duh, but right. I'm sure a lot of you saw that coming. Like if you put a bunch of oscillators, just bear with me. I know I'm like 1 minute over time, or if you have to leave right now, leave. But I am done. The point is this. If you put a bunch of oscillators that are identical in every way, except they're separated in phase by a constant step, and you let them go, if this one goes like this, and this one goes like this, and this one goes like this, but they're all out of phase by a constant amount, what do you see? You see a ripple horizontally propagating through the ensemble. Each one of these objects is only moving vertically back and forth in a small neighborhood, but a pulse, a crest, a trough, a hump propagates, a shape, a disturbance propagates horizontally through the whole thing. That's what we call a wave. It's not an object. There is no spring that actually moves through, all that's moving here is metal. All that's moving is metal. And we see something moving from over to the left all the way to the right. We see something moving horizontally, as you did in lab 3, but there ain't no piece of metal moving horizontally. This is an unthingy thing. This unthingy thing called a wave pulse is composed of a collection of identical phase staggered oscillators. If you really understand oscillators and you understand phase and you see how to put them together in this way, mathematically and physically, you now have a wave. That's what I want you to portray to me in question 4. Again, there's more expanded versions that I posted, but this is what and that just went crazy. That's what I'm looking for. I want you to show me that you can see how what a wave is, an unthingy thing, is composed of oscillators collected this way. And sorry, I did go over time, but last thing, why am I calling it a wave? Like, why is this? Besides the fact that it looks like one and you can recognize it as one, the key point to say in English is all that is moving here is metal. But something observably, measurably moves from left to right. Something moves horizontally. It moves a certain space in a certain time. You can time it. You can measure its velocity. You can use its velocity to predict where it's going to be next. It's real. A wave pulse literally does move horizontally. However, the only materials in the physical world that are moving are pieces of metal, and no metal moves no piece of metal, no particle goes from left to right. Only information, only a disturbance in the medium of metal flows from left to right. This is what a wave is. It's a collection of phase staggered oscillators. You've been super patient. I'm not going anywhere, but you totally can go. But that's the exam. Check out the other videos. You've been very patient. I'm not going anywhere, but thank you for bearing with me for the extra 5 minutes. I owe you 5 minutes and I owe you points. Okay. Okay. I'm done. I'm going to fix that. I'm going to breathe for a second. Again, you can stay. Hold on, just fix it. And I'll post all this, obviously, in the chat. So, wait, and let me hold on. Sorry, I'm not going to stop the recording because you might ask something that might help someone else. Hold on, let me just change the view. But I believe, was Christopher still here? Oh, a lot of people are still here. Okay, you can go, but you can also hang out. I'll hang out until okay, thank you. Okay, have a great day. Yes, have a great day. Okay, so I'll pause for everybody. Anybody who wants to stay can. It's totally it's totally optional. But I just don't want to leave you hanging. Okay, thank you, and thank you for showing video.
Okay.
Have a great day. Have a great day. Have a good one. Yes, I'll still wait. Okay. Okay. Should I stop the record? I'm going to stop the recording. Oh, thank you, Tariba. Awesome. Thank you.